somehow. This is why mathematics seems like magic to some people. And what you're saying is correct, Kate. What you're saying is correct. The problem is we need a quantifiably logical and procedural way of understanding why this somehow works.
It works better than that in my head.
No, good. No, what that means, Kate, is you have internalized the procedure. That's a good thing. But what I'm trying to do up here is I know there are holes from our previous classes coming into this class. We've got holes in our learning from before. What I'm trying to do is kind of plug up those holes with a problem like this. It creates these kinds of discussions. So, okay, go ahead.
With the problem of c squared over pi divided by 4, can you just write it out like...
I'm going to take a little U-turn here. Okay.
I have a quick question.
Yes, quick question.
I feel like that should still be pi squared.
This, even after we knock this off.
Yeah.
Can we take a second U-turn to show you why it's not?
I need you to.
Well, yes. Well, take your time with me next time you come here. So, U-turn. Okay, let me erase some board though. Can I erase this stuff up here? Just because I can go straight up as opposed to L-ing around. Okay, good. All right, so let's take care of all this. So let's analyze just this piece right here. So you've got pi over 1 times c squared over pi squared.
All over 4.
Well, let's forget the over 4 for a second, because your question is the pi, not the 4.
Right.
You're okay with the 4 being there. Let's write this, instead of as individual fractions, let's break it out into its individual factors. So this is really pi times c times c. And this is 1 times pi times pi.
Thank you.
Does that make sense?
Yep.
Exactly. So that's why when you knock that one off, 1 goes away. And that's why I just took the exponent away.
Thank you.
This is good. This is why. Do you see why I like this problem? This is why I like this problem, because it answers all these little inconsistencies or little tiny things that were missing in the previous classes. So we're happy with that. We're happy back here. Good. So now, back to Gabe's U-turn, which I love. Let's analyze just this piece right here. C squared over pi all over 4. The trick with this one, I love the way Ben described, except I don't know how to draw c squared over pi to make it not confusing. Like with 1, I can draw a circle, and there's a circle, 1. But c squared over pi, I'm just going to leave it c squared over pi. So we're going to default to Gabe's method. Using this, it's the same as c squared over pi times the reciprocal of 4, which is 1/4. So you end up with c squared times 1, which is c squared, over 4 times pi, which is 4 pi, which is exactly what you were trying to show was equal to. Equals. So there you go. So it's the process. Think about how many different math classes worth of information you just used in that. Pretty much everything you've been in since you've been here at COCC is involved in this one problem, i.e. why I like this problem so much. Once again, why I like this problem so much. So when you guys that are in natural resource management, or you guys that are in forestry, or wherever you're at, have this tabled book of formulas, you have some way of understanding why the formulas actually are the way they are. I mean, there's a reason why these formulas exist. This is justification. It's also useful because it gives you a way of figuring out how big a pipe is if you forgot your calipers, but you have a piece of string and a tape measure, which you probably have in the back of your truck. You might not have calipers. You might have a tape measure, a piece of string, or a belt, or something you could tie together to make a flexible measuring device, or something you could, there's all kinds of wonderful little field tricks like this one. Echo, go.
Would that technique work with non-circular items like ovals?
Yes, my friend, great question. You'd have to adjust it for the area formula. So Echo's question is, suppose the tree wasn't perfectly circular, suppose it was oval. So a circle has this very specific pi times the radius squared. An oval, or an ellipse, we'll call it an ellipse, I think it's a technical name for it. We'll talk more about this momentarily. It's got things that are called foci, which sit out here. Okay, and that's the way you can draw an ellipse. Has anybody ever been, there's a bench in Portland that's shaped like part of an ellipse, where you can sit at one point on it, and your friend can sit at the other point. And if you whisper, your friend can hear you as if you were sitting right next to them. Has anybody been to that bench in Portland? There's also a thing called the Whispering Hall in Washington, D.C. Has anybody been to that? Whispering Hall? You check that out. Whispering Hall is shaped like the top half of this ellipse. Yes. So if you take away the bottom half, you've got this floor and these two focal points. I think they're actually further out than I'm making them look. Yeah, so you put your friend here, and you put your other friend here. This friend whispers, "Hey, how you doing?" And it sounds like they're standing right next to you over here, because it bounces up, the sound wave bounces up and heads directly to where the other person is standing. No matter to which direction you aim that wave, it will always reflect back to that focal point. That's what the definition of an ellipse is. A circle works the same way. If you've ever walked into the basement of the library, going down towards testing and tutoring, down the staircase, you come around and you step out into that little foyer area that's right there, it's a perfect circle. Hum to yourself the next time you walk through there, like towards the bathroom, just go through humming. When you hit the center, you'll hear your own voice in your ear. Not that you don't already, but it'll sound like it's coming directly in, amplified. Because what's happening is as soon as you cross into that center, it's going out and coming straight back and hitting you straight in the ear, as opposed to going from your mouth up to your ear this way. Try it next time you go to the basement of the library. A circle is... What?
Everybody already thinks I'm crazy for talking to myself.
I'm saying to hum. Don't talk to yourself. Well, talk to yourself too if you want to. A circle is basically an ellipse that's collapsed upon itself. So basically, what you'd have to do, Echo, is you have to measure these things called major and minor axes. So the area of an ellipse, the area of the ellipse, is actually pi. This is usually called A and B. It's pi times AB. In a circle, A and B would both be called R. So it's pi r squared. So for an ellipse, it's just pi times AB. I had to use that relatively recently when we built our pond in our backyard. I had to figure out how much water was in the pond. And the pond itself is oval, not circular. It's oval. It's 22 feet by 14 feet, average depth of about 2 feet. So using those measurements of 11 and 7 and 2, I was able to measure how many cubic feet were in the pond and then multiply that by 7.5. That's how many gallons were in the pond, figure out how much like a pump I needed to actually have the whole thing run. This is why people think I'm insane. Because I don't just pay somebody to do that. but I mean, so yes, you can, for any shape you want, as long as you can find the area of it, you can do the exact same math we just did. It might not be as neat at the end as what we just did, because some of the things that happened were a consequence of this being squared, right? That is one of the consequences. So it might be messier, but it's still possible. It's still and very useful. And very useful. You could extend this to 3 dimensions. And figure out, for example, that coffee cup right there from Dutch Brothers or wherever else. This shape is called a frustum. So you have a cone. Imagine an ice cream cone coming down to a point. If you take the cone and lop it off, you create what's called a frustum of a cone. So you have to figure out the volume of this. Why? Because you have to make sure it holds 12 ounces of coffee. You know, at least, there's not a little bit more to make sure that people don't, sue you for giving you 11.3 ounces of coffee when you pay for 12. So there's all kinds of mathematics involved in this stuff. I mean,
16 ounce.
16 ounce. Well, then I hope they're at least 16 ounces. I thought you weren't looking very much at that. Good for you. Make sensible-ish? Yeah? I know it's a lot because it's making you call back to math 10, math 20, math 60, math 65, probably even math 95. But that's exactly the kind of stuff I want us to become comfortable with so we can be conversational about it. Might you forget it again? Sure, you might forget it again. And we'll do it again then if you forget it again. We'll pick it up as we need it. But as long as I see, tell me your name one more time.
Me, Janaea.
Janaea, when you said, oh, as soon as we took that little branch out, you went, oh, done. That's why we do it. Because all those little tiny revisits just firm up those synapse connections even more. Makes the fire more efficient. Yeah? Okay, let's take 5. Let's take 5, yeah? Let's take 5. Give the camera a break. And then to you guys.